Good morning, my outstanding friends. I am thrilled today. And why am I thrilled? Well, I have a lot of people sending me things, pictures and questions and all that kind of stuff, and asking me to explain how I can make these statements I'm making and stand behind them and support evidence when they see something like this. Seashells. They claim these are seashells on the top of mountains. Where did they come from? Because my claim is, right now, I feel very confident in saying that I can literally account for the entire geology of the Earth based on the mineral content, the striations, the formations, and mostly the chemistry. Because the chemistry relates to body chemistry, biochemistry, and that's what I understand very well, and I understand the anatomy extremely well now. And I can put them together and tell you these are not clams. That, my friends, is a lung. And these are the alveoli. The black, the yellow, and the red are the colors of iron oxides. Well, what are iron oxides? Iron is your blood. Iron, your blood is made primarily of iron. Now, is it just one big thing of iron? You see like a chunk of iron? No, obviously it's in fluid, and it's mixed with these oxides. An oxide means different levels of oxygen attached to different iron. And as they move through your body, they drop off oxygen. They come back and pick up some more. That's how you get your oxygen into your body and release your carbon dioxide and so forth. And it happens inside of lungs, and it's filtering through these devices right here nobody knew about. Hold on one second. Okay, my friends, nobody was injured in the mic drop. Now, this is all factual material evidence, chemistry, biology, anatomy. There's nothing here that can't be understood, but it needs to be examined and looked at for what it is. As I said, I claim this right here is out of the lungs. The black is iron oxide, which is the magnetite of iron. This is the hematite. The red is the hematite. It's changing its states in here. Now, if you think these things can't look like this and preserve like this, I'm going to show you a lung right here. You see that? That's a lung. It's growing some moss out of there or something, but this is all lung tubing, and the black is the hematite, the magnetite, and the red is the hematite. All right, now when this was taken out of the ground, all he could see was this. He broke that open, and then this was Gary Evans over in England, and this is from Angela. She's down in West Virginia. This is all. Everybody said, well, where did all these clams come from? They're not clams. They're not clams. And I'll show you they're not clams, and I can literally prove it. And the state of blood in them is undeniable. I have them in a microscope. Actually, she sent me some. You see that? Yellow, black, and red. That's the three states of iron oxides transitioning in the lung of a creature. We're going to look at it right now. And I have a whole ton of stuff to show you. But clams on the side of mountains, no, not necessarily. There might be some. I can't say it's not. But these are not. Okay, my friends, today I promise I will show you the microscope shots of this lung transpiring, which was thought to be some kind of a clamshell. I have it in a microscope here, and I'll show you what these things really are. And I'm making some outrageous claims if you put them against what normal geologists would tell you. However, these were from creatures that are just beyond the belief of the professors and the institutions that are teaching, because they've been so deeply indoctrinated, really, to be just as dishonest, that they have to say what they're told to say or they're dismissed. It's just the way it works. So I am showing you what I show you. You make your own determination. But don't, I never could stand to acquiesce to somebody just because they stood over me and said, hey, you do what I tell you to do or you're done. I said, well, I'm done. And that's just happened when I was in the Army. That's a whole other story. That was hilarious. But anyway, you got to stand up to say what's real. This is killing me. 15 years of just that total denial of reality. When I say denial of reality, I mean denial of even examination of factual evidence supported by way more than they have. This is all stuff that can be examined. It can be chemically tested. It can be verified in a whole very ton of ways. And I did a DNA test and a CAT scans on my giant body parts from giant creatures, giant humans they turned out to be. I have some that are just standard size. I have tiny little ones. I have ones that have different looking feet than ours. And Yale did a thing on this, and they call these Edicara biotas. All that means is they think they were slimy creatures, had no bones or anything. That's just totally wrong. These were giants, and this is what's killing them. And that's why Yale has turned away from this, because I presented this to them 15 years ago, and it's been nothing but denial from them. And until they published their own paper saying, yeah, this happens, but it's only creatures that were before any real life on Earth. They were wiped out. And it might have been what do they call it? It ended up being a great flood, really, because it was one layer covered the whole Earth. It was the Triassic. And after that, normal creatures started to come, is what they say. Before that, it was just slime, nothing but gooey things. There's no bones, there's no teeth, there's no shells. Totally wrong. And again, I presented all this to Yale with the DNA and the CAT scans and the whole 9 yards, turned away. Then they wrote their paper a year later that basically said, yes, this is all true, except it's only slimy things that would do this. No, totally wrong. As you will see, I'm going to show this in extreme detail, and they were giants. That's what freaked them out. As far as I'm concerned, that's a fact. Okay, my friends, I'm going to try to stick to the routine today. We're going to look through all of these different body parts and see the blood chemistry. And we have to go and actually look at the chemistry, because it talks about these iron oxides. Like in the metals, in the iron oxide is a key component of hemoglobin, hematite, the same thing. It's iron oxides. Fe is iron oxides. Hematite is red, brownish color, yellowish red. That's an oxide. That's the hematite, the red. The magnetite, typically black. Yes, black, yellow, and red. Those are the states of iron oxides, which I show extremely clearly. I mean, you can't get any clearer than this. I have them right here in my shop. I'm going to show you. Well, here it is in the microscope right up above. We're going to be looking at it right now. So get ready. I got to turn the lights off. Oh, my friends, this is just so far out of control. This is up on the top of Angela's Mountain in West Virginia. And she says she's up on the top, and this is right up there on the top. Now, she sent me this and some other stuff, a bunch of these little bits and pieces. This one here, we're going to look at in a microscope in a minute, and we're going to look at this. You see this? This is what's inside. Well, inside of what? You see this? We're going to be looking at this in a microscope. You look at that and say, oh, those are clam shells or whatever. This was just a seafloor. Well, and then you would say, well, that's the bottom of the seafloor. and they were just laying on it like this. Oh, these shells just collected there. That's why this is a totally different substance than this. Well, I say no. This is the coating, which was the pleura on the outside of the lung, and this is the inside of the lung. And can I show this, that there's a pleura around the lung cavities? Absolutely. Because here's one right here that has the pleura around it complete. This has been DNA tested and CAT scan. And that's the tab that locks it into the body. It's called the spur lock. I drilled a hole in here and took blood out of there. Deep inside, not on the surface. It's DNA tested. Flat as a pancake because it was in the Great Flood. Now, this came from the Great Flood too, but it was from a giant. And the top of the surface of the giant's body eroded and left up the top of the lung, and underneath is these. And in areas, they're open like this. And when they get wet, the blood turns into, like when I put water on here, you're going to see a completely different situation. And we can see where the pathways of the air go. And you can't hardly dismiss any of these things I'm saying if you look at it. Now, again, that one I just showed you here is completely encapsulated with the pleura. That's this heavy-duty rubbery stuff that goes 24 hours a day, or you become deceased. Now, this is that pleura. It's just a rubber bag. It's just a big rubber bag. Some of it's eroded away. That's down in where this stuff is. That's down where the alveoli are. All right, and there's a little latch on this one, too. That latches this thing into the body. So they all have that. Now, we're going to look at this in the microscope and put a little water on it, and you'll see the difference. And this is the inside of a giant's lung. And I'm going to show you something. Watch this. I got everything. If I ain't got it, there ain't any of it. That's mine. This guy died like this. This is the guy's lung. Somebody's lung. He died like that. These are the cavities of his lung. And if you smash this open, well, you don't have to. I'll put it in a microscope, you'll see. But he died, and everything rolled off of him, too. Down into this, it would be the same thing. And then there's mud around it, which is the fleshy stuff. And if you go down into his body, you see, this is the lungs in here. These are the lungs, the alveoli. And then you get down to here, where's his backbone, and there's still some bits and pieces of backbone in here. All right, he died laying flat like that, and after all eroded away, you know, the skin and the flesh turns to mud. That's all it is. It left the lung laying here. Now, I would like to do some chemistry on here and smash open these lobes because to see if we can find sulfides. Because they ran over something almost identical to this. I mean, it is identical. Up on Mars with the rover, and it smashed open. They said, wow, look at all those sulfites or sulfites or whatever they were. There's some kind of sulfur molecules inside there. So I should crack that open, and we can look inside and see if we can see any yellow crystals. Because I believe that's what we'll see if it's in here. You know, that's up on Mars. I don't know. But that's what happened. This guy died. That's a body, that's the lung of a creature. And there's some red blood up in here. You see? Most of it ran out. If I put water on it, you'll see red blood. Most of this has been totally all the red blood has run out, almost 99% of it. If I put water in these areas and put it under a microscope, you'll see red blood. And up there, there's no question you can see red blood. I know what these things are, my friends. I've been doing this 15 years, and I rarely can miss anything anymore. It's just there. My friends, prepare yourself. This, as I showed you, is nothing more than a batch of alveoli inside of a lung. I don't know if she realizes that she sent me the outside of the lung, which is the pleura, and then right into the inside. It's amazing what people send to me. I have things that I would have never even thought to, that's a big chunk of blood leading in there. These are all tubes leading back. Oh, my friends, this is going to be fun. This, again, is the inside of the lung. That's the outside. That's where the outside of the lung is. These are the alveoli inside. And that is a big tube of blood, I believe. And all of these fan-looking things, or seashell-looking things, are blood absorbers. And I can show this in so much detail. Now, I have this in the microscope up above. I have to turn the lights off before you can see it well. Hold on. All right, if you've been around mud fossils, you know that the black is the vein blood and the red is the artery blood. And you have to change. You have to get the red blood has to absorb the oxygen, and the black blood has to turn to red. They just cycle around. It's their oxidation states of iron. What is an oxidation state? It means same iron, but you add another oxygen, it changes the state to oxygen 2 to oxygen 3, that type of thing. So all it is adding another oxygen, making it turn from red to black. And the red stays fluid, runs all through your body. The black turns solid as it comes out and turns hard in the mud fossils. Now, look at this. Look at that amazing webbing there. All of that is like, almost like a filter to absorb the oxygen is all I can say, because this is not bulbed out. This is a scooped in. Hold on, I'll move it a little bit. You see? It's scooped in. And down here is where the transpiration, or whatever you want to call it, happens. Right there. And these, the red and the black, and somehow the stem, I don't know. We're going to look at it a little better. But this is red blood, and that is black blood. I don't care what anybody says. It could be tested. I don't know what kind of blood it is. Hold on, let me focus in there. But this is what happens. This stalk comes out, and it leads right up through the center, and they fan out. There must be oxygen or air in this area, and it's sucking it all up and sending it to wherever, through the body. This whole area is just loaded with all of these fans. You see, there's another one there, another one there. And the yellow is, you got black and red, and then there's the yellow state is in between the two. And she had some fabulous shots of the yellow. Hold on a second. But you see, that's the coating around the lung. And they all have a coat. Everything in your body has a membrane. Your lungs have a very thick membrane because it's got a big rubber bag. You got to protect those lungs. Okay, my friends, I got the work made out. When I get this out, I can angle everything. It gets serious when I get this out. Now, what are we looking at here? Check this out. Check that out. Well, what is that, Roger? Well, look at this carefully. Look at this. And then look at this webbing coming out, which wraps around these clamshells, which I say are not clamshells. I say they are alveoli. All right, now we're going to see how important moisture is and the variability of light. I'm going to put a little moisture on here, and it's probably going to sink in almost instantaneously. You see it going right down through the cracks. It's exposing some minerals here. And of course the blood and the textures. I'm going to turn it up a bit. And all of these little stripes, I think you can see. But notice the tube that comes in, and then it's flaring off into these clamshells. Now check out the colors as it dries out. What that is, I don't know. But look at the stuff that's inside of these lungs. These are like organelles or something. I'm telling you, this is a lung. These are like, I don't know. This blows my mind. And then you see the red, and then you see over here where it's turned into yellow and black. You see all the real red and yellow. Let me turn the lights down. Here's where the key to seeing things is in the different intensities of light. You see how red that is? See how black that is? The green is probably copper. Can you see that? Yeah, you should be able to see that good. And the black is the magnetite, and that's the hematite. And these are, this is right in front of you. I'm moving this. I have this in my hands. Angela was so excellent to send this. Look at this. These are little branches of tubing that are inside the lung. Look at that. Angela, you are a sweetheart, my friend. You are so good to have done this. Because I have been plagued by people saying, oh, there could very well be seashells on a mountain. I don't know. Because the whole earth at one time was virtually an ocean during this event that killed all these gigantic creatures. And they're just gigantic creatures. It's the way it is. You can take it or leave it. Sup to you. Now, where else can we look over here? Let me go find something really interesting. Hold on. This just stunned me. This is one of the anchor balls. And this is how they invest. If you're looking up through the bottom, looking up, on the top they have these little dimples. And nobody's ever really realized what they were, because underneath them is these tendon balls. And that's what this ball right here attaches to that tab. You don't see it unless you really can play around with the lighting and see. You see it now, you can see it quite well. This is where this thing invests, and that tags it into this fabric at the top, which is the interstitium, basically the fabric that wraps the lungs. All right, and that's what we're looking at here. Now, I am going to try to move this freehand, and then I just want you to see where this is coming from. This is the surface of the lung. All right, it's pretty well eroded down to where very close to that surface is going to be where these things start. Now, let me turn up the light. And when I say these things, I mean the shells. All right, right there. Hold on. This is where the shells start, right underneath. But that's the ball that holds the interstitium so that it can stretch and pull and do all this, and it will always come back to where it's supposed to be. See the ball? Here it is right there. That's what holds the interstitium in place, you see? That's the whole surface. It's all collagen fibers, and I mean there's a bazillion of them attached to these balls. And that's how your lungs can stretch and pull back and forth. Now, if I go down with the lights, you can see the difference in the colors. And I believe you should be able to see that. Now, if we tip this over to the other side, underneath is where all the alveoli are. All right, and you can see how vivid the colors are. When I tune this in and I put some water on there, it will blow your mind. Now, I believe that's copper. I'm almost certain of that. I did some tests. Hold on one second. I'll show you what I did. Now, you saw there was green in there a little bit. I did some tests a long time ago of actually putting electricity, DC current, very low, like a 1.5 volt battery or whatever it was, and some solution to see how I could make the mud fossils. And at that time, this did not create the mud fossils. So I went on with my life. But I kept these to show the invasion of the copper, and that's all it was, because this is copper wire. That's all it was, copper wire, heavy-duty copper wire, and that's what happened. So anyway, that accounts for the copper as far as I'm concerned. And when you look up about the different blood metals, copper is very prevalent, and zinc is as well, as iron is almost exclusively iron is a big deal in your body, let's put it that way. And especially when you start running, jumping, and exercising, your body pumps blood like literally gallons, I think, an hour. I mean, could be a minute. I don't know. I got to be honest with you. I can look that up. Wow. It's even more than I thought. Listen to this. The human heart pumps approximately 5 to 6 liters per minute at rest, just laying around doing nothing. That's about 1.3 to 1.6 gallons per minute through your body. During intense exercise, it can increase significantly, reaching up to 20 to 25 liters per minute, 5.3 to 6.6 gallons. You can't even pump that out of a gas station. Trained athletes, however, the typical range for most people at rest is about 1.3 to 1.6. Wow, that's a lot of blood. Okay, this is from our Chat GPT friend. It says, many metals are present in trace amounts in blood. Many, almost all of them. But not every metal is found there. Now, essential metals like iron, copper, which I just showed you, the green stuff, zinc and selenium play important roles in biological functions. They all play important roles, and here's why. All right, I'm not going to get deep into this because everybody's, oh, there he goes to the chemistry again. But if you don't understand the chemistry, you don't understand how blood works, you don't understand how blood works, you don't understand how these different states occur and these different colors occur. These are the transition metal ion colors. As they change states, and you can add 2 or 3 or 4 or 5 of them together, and they change to all kinds of colors. I mean, you know how crystals are. This is all the things that form crystals and so forth. And they are inclusions in silicates primarily. Now, what you have is a metal core, and that's one of these. And around it surrounds what they call ligands, which are attachments to other molecules. And as that goes through your blood, these different charge states, they give up little bits and pieces, and then they take on the carbon dioxide or whatever, junk. And they bring it back and they recycle from the black to the red. And that's the metal core. And this is in aqueous solution, means watery. Transition metals form colored compounds and complexes, very complex with all these little particles around it. The colors can vary, all kinds of colors, depending on the charge on the metal ion. The number and type of groups of atoms called ligands, what kinds of them are attached here, because they can attach to a whole series of different ones, but this one will affect that one, and that one will affect this one, and that one, and so forth. They'll make a certain pattern of charges to other molecules, put it that way, and drag them through your body. Now, they attach to the metal ions, and they're called ligands. That's a ligand. In aqueous solutions, watery, the ions form complexes with the colors shown to the right. An ion means it's not the actual titanium. Titanium, let's say, is 100, which it isn't, but let's say it's 100. Well, this is 103, or it's 97, one or the other. But you want to be at 100, so this is a charged particle. It's got too many electrons or not enough. So when it goes through your body, either dump some off or it picks some up. Simple as that. And these are in your blood. And they're everywhere. So if you don't understand this, you got to understand a little bit of chemistry. It's not hard to understand. There's your iron right in the center of the transition metals. These here are the transition metals, the blue ones. They're all the way through your body. Copper, magnesium, chromium, zinc, and I showed you the copper. Hold on. You know, I'm going to brag because Mudfossil University has the best researchers in the world and has more of them than anyone else. And they're not getting a penny. They're doing it out of the interest of truth and trying to find out, what is this, what is that, what's this from, what do you think about this? I get this on a very regular basis, and the people that are asking these questions are invested in wanting the answers of the truth. They don't want to be, just say, I'm saying this is what it is, and you're going to have to tell me it's what I'm saying. No, it is what it is. You show me. Gary Evans sent this. He found this on a beach over in England. He saw this, and I think he saw that little thing hanging out, and he said, well, I wonder what that is. So he broke it open. This is what was inside. It's a lung. You see that? You would never know that. If you looked at this, you'd say, well, that's just a rock with a bunch of little pebbles stuck to it. No, that is the outside pleura of a lung. There's the outside pleura. This is the inside of the lung right here. All right, and inside all these little things are the alveoli. Now this is transition, and once they get like this in the salt water, in the mud for forever, the salt water really tears them up. But you can see, I mean, the blood is still here. There's just blood comes still in there. There's some kind of sea things growing in here at the same time. But now, again, this is nothing more than blood that was in here and all the tubing. So the tubing ran to the alveoli. And what do the alveoli look like? Well, they look like this. So all these little tubes are going to run down to this. Now, remember this? Do you remember this? I showed this before. This little tubing running around like this down into this network. I showed that on the stuff Angela sent me. She sent me some of the most fabulous stuff I could even imagine. And she actually showed the whole outside of the pleura that surrounds the lung attached to this. How she came up with it, and the people that send me stuff, it's stunning, absolutely stunning. Okay, I just splashed a little water on this. That's in the microscope. I'm going to dry it up just a smidge. Now, again, I say that is the alveoli absorbing the oxygen and blowing out the carbon dioxide. And in the exchange, it creates different oxidation states of the iron. That's how they do. They give up. Now, I find it interesting. There's a lot of green, not a lot, but a significant amount down in here, which is the iron, the copper. I'm almost certain of that. And these are all these little wells, as I will show you right now. Wait till you see this. Check this out. This is one that I did a close-up with a microscope. You see this tube coming in, flaring off like this? Look at what it's doing. It's got this wrapped around it, and then it flares off in these tubes, which are absorbing and changing from the red to the black, and they have the green in with them as well. You see that? That's not wet, that's dry. But you can see these are the muscle bands. You think I'm kidding? Well, what can I show to prove it? Well, there they are right there. These are those little muscle bands, I'm telling you. And they come down to these holes, these cavities. Now, these are not the cavities that we're seeing, the egg seashells. Way in deep here is the seashells. All around here. This is just where the air passes through these big balls from one to the other. But then where they wrap around out here is where the capillaries are. And you see the black and the red? Well, in the body it's blue and red. But when you expose it to more oxygen, it turns black and red. And then, and that's where all of these elastic fibers. We're looking at the elastic fibers. This is what they show them as elastic fibers. Well, they're doing something, I don't know. But what we were seeing is that exact same structure. Here's where the muscle bands come down and the air tubing comes in. You can see it's totally different, and up above is totally different. And it comes in and it flares off to these different colors. There's the green, which is the copper. Now, copper is interesting, but I know it's required for, I forget, hold on a second. Another mind blower. Listen to this. Copper plays a crucial role in cellular respiration. Everything is cellular. Primarily as a cofactor. It's needed in addition to the enzymes. Enzymes are what does everything basically in your body. Enzymes are the things that break things down and build things up so fast it could never be done. You could never live without the enzymes. Impossible. Now, this is why copper is important. Enzyme function. Number one, copper is essential for enzymes involved in electron transport chain. There they were, right in the lungs. It's a critical component of aerobic respiration. Critical component in the lungs. These enzymes help facilitate the transfer of electrons and produce ATP, which is adenine tryptophosphate, the energy currency of the cell. You need that to make your cells work. So copper sounds pretty important to me. Copper can easily transition between oxidation states. That's what you need. I thought it was strictly the iron, but the iron apparently works, well, here it is right here. Copper easily between the oxidation states, allowing to participate in the redox reactions that are vital for energy production, which is the enzyme part of it. Now we go to iron metabolism. Copper is involved in iron metabolism, which is important for the hemoglobin production and oxygen transport in the blood. There it is right there. Further supporting cellular respiration and Mudfossil theory. It's an antioxidant defense. Copper contributes to the antioxidant defense system, helping to protect cells from oxidative damage during respiration. That's interesting. Overall, copper is a vital trace element that supports various biochemical processes, including for efficient energy production in living organisms. Well, we just saw it in the lungs. That much you can't deny. It's right there. And it's all, everywhere in these lungs, we're seeing some of this. We're seeing every bit of the chemistry that I talk about. And I'm going to show you in the microscope a little more. But there it is right there. Now, you wouldn't see without the microscope the copper, but we can see with the microscope the copper is quite obvious. So let's do a little more micing. Okay, this is the lung. We're stepped quite a ways off. The microscope's way up here. But these are such big lungs that we'll be able to see the alveoli quite easily. Now, I'm going to have to turn the lights off, but that's what we're going to be looking at right there. That is the microscope. All right, and to prove it, I will wiggle it a little bit. See it wiggle? All right, now, like I say, we're stepped off quite a ways, but we're going to take a look at this. I'm going to put a little moisture on there. We're going to change the lighting. That makes a big difference. When you know, certain colors reflect at certain different frequencies. But when you put water on it, virtually everything has a little better glow to it. Let me put it that way. But these are these shells, and they're being fed by little air tubes that have these wrappings around. I think I showed you those. All right, I just put some water on. It absorbs it pretty quick. But you can see all of these little filaments all over the place. And like I said, we're a ways off, so I'm going to home in closer. But you can see the colors transitioning from black to red, using the copper for a cofactor. I don't know. I'm going to dig way down into it, so I'm going to have to do some adjusting. Hold on. This is too much. This is one of those little fans. That's where the blood, the red blood, which is the artery blood, is picking up its stuff. Now remember this tubing that has the wrap around it? Hold on, let me focus in. There's the tube right there. Let me focus this in. That's the tube running into the another alveoli. I'm going to have to move this down. And there it is right there, where it flares. There's the wrapping of the right into the alveoli. Look at that. This just blows my mind. Absolutely stunning. Stunning. You see the different colors? If I do this, it'll stop in a second. Oh, look at that. Wow. Look at it. That's the key of having the scope here that gives you these different, intensities, so it's not overwhelming. Look at that. There's no question that's the copper. I mean, this should be easily tested. And that is the magnetite blood, and that's the hematite blood. And this is, they're in the transition phases. I'm turning up and down the light. Now, it goes out to the flare, which is this whole scoop. It is what it is. And that's what solves the puzzle of the seashells up on the mountain. This is beyond my wildest dreams. I can't believe this. This is beyond my wildest dreams. I could have never, ever, ever expected this. I mean, look at this. It's all twisted around and around and around, and it turns into what is going to accept the stuff coming back. So it's not just the muscle bands, I don't think. But I could be wrong. So maybe they're talking about muscle band and they don't realize it's actually absorbing, I don't know, or emitting, I don't know. But that, I'm 100% sure, is iron, red iron blood. And this appears to be the black. And you got the copper in this area, and you got some copper up here. Could something be in between the two? I don't know. I got a lot more digging to do because I just came into this. Angela sent these things to me a couple of weeks ago, and I've been really tied up with a bunch of things, and I thought, wow, I'll get there, and I just didn't do it. And I said, whoa, when I saw this, yikes. Yikes on steroids, yikes. These are the alveolar. All right, so you're an explorer. Stay with me. This may take a little time. We're going to go right down about as far as I can go. This microscope doesn't really do deep details, but it gives a very clear look, and you can focus in and out. What these things are here, I don't know. I mean, I know that's got something to do with artery or whatever. All right, all of this is all tubing inside the lung. Let me back out of here a little bit. Let me be too close. There is actually quite a bit of copper in here. And these are absolutely, there's no question in my mind, this is from the lung. Absolutely no question whatsoever. And it's just loaded with the chemistry of lungs. Look at this. Let me come down here and see what's going on there. There was some like round ones just laying around. This is the way we discover things, my friends. I told you I'm going to drag you through this with me. What's this over here? All of these things, these are not these structures for nothing. And this right here is spewing out black blood for some reason. You got copper here. This looks pretty red. Let's see what's going down here. That's obviously some artery area. When you see the red blood like that, it has that oxygen level where it could be just getting transition in here, because it's still got the dark brown and then you got the really red. But I believe it's pouring out of that area right there. And the whole thing is, at one point, was an artery. And then you got other ones that are just black as black can be, because they're from the veins. And they don't have the same kind of, they just pile up and turn into a little hard spot. Look at that. That is the chemistry of lungs, my friends. That just didn't happen by accident. Watch, we can follow that one right up to where it's a bunch of blood. Hold on. Look at this. Not clamshells. Angela, this is fabulous, my friend. Fabulous. I never expected to be able to see such exquisite detail of how these things are formed. And this opens up, you know, this microscope is not bad, but it's not what you want to have to examine this and all the different possible ways to look at this. And, you know, I have only limited resources here, so. But as far as I'm concerned, no question, that's a lung. All right, so let's examine the pleura. And what is the pleura? Well, that's the surface that surrounds the lung. And that's the thing that has to do this and that all day long. And it's made out of all of this fibrous stuff, which is pretty much completely eroded. There's still some black balls left in here, but very, very few. Now, this was the coating, and inside was those alveoli. Now, let me turn this up. You see this is in my microscope right here. So we can see some of the little tendon stuff and the bloody fibrous stuff that would have coated the lungs. Let me come in real close on, well, you don't have to see it. I'll show you what a normal lung looks like that has not eroded as much as this, because this is heavily eroded. And if you tip it on the side, is where you can see there's the surface. All right, and those little black balls are what holds the fabric together, really. But almost all of them are eroded away. Now we're down inside the lung. Hold on, let me. See that? Look at that. There's a tendon ball right there. How fortunate was that? I mean, come on now. How cool is this? This is one of those clamshells, which is an alveoli. It's the blood or the air or whatever. However it happens, I'm not certain. But somehow in this passage of these fluids, the black turns into the red, is all I can tell you, because we use it. Now, the copper, as they say, is a coenzyme. So you have to have certain enzymes. What they are, I don't know. And then you also need copper to make that enzyme function. What does an enzyme do? It makes chemistry happen literally up to millions of times faster than it would if you didn't have the enzyme. You don't have the enzyme, it's not going to happen. So you can breathe all day long. you don't absorb the oxygen. Well, why aren't you absorbing the oxygen? Because you don't have an enzyme to break down the molecules into what they call isotopes. And then they begin to decay into daughter isotopes, which give up oxygen and so forth. You need oxygen in your body, and you need a ton of it. I think I told you, you pump just sitting around 1.5 gallons, something like that, of blood a minute through your body. And that's going through there, picking up oxygen. And of course, delivering other things through your body, but primarily in your lungs, it's oxygen and getting rid of the vaporous, nasty gases. All right, you want to see something outrageous? Wait till you see this. As I say, all of these things are blood. Well, blood has not just iron. It has all different metals. Like they say, not a ton of them, but it has, we can see there's a lot of copper. Well, what other ones? Well, look at this. This is, I guess they call it a spectroscope shot of lungs. This is by Bristol Myers Squibb. And here's those channels coming in, feeding the alveoli. And look at all these different colors in there. Well, why? Why all those different colors? And look at these little bands coming down. This is exactly what I was showing you. Why all those different colors? Well, because they're the different colors of transition metals. I showed you the transition metals. All right, here are the transition metals. And they can make every kind of color you can possibly think of. And where would they collect? They would collect in those alveoli, in these little cavities here. And if it was a giant creature, they'd look like that. I'm pretty sure this is natural. I can't verify it for 100%. People send me all these things. They say, what do you make of this? I say, wow, it looks like the fabric of a lung, and all the transition metals have collected, because they'll concentrate. They'll find each other. They know how to get together. You know what? Let me show you something. These are almost like opals. All these different colors, they could be turned into crystals. They're rounded in the ocean or whatever. But they are a concentration of certain chemistry. Like this thing right here. You see how red that is? And all these different colors. Now, that one there looks like a crystal already. But these kind of things are natural, because they're concentrations of transition metals. Now, this had to be where there was a ton of blood, and it was sequestered for a long time, and they all found each other, and everybody was happy, and then somehow it got washed by the ocean. That is my thinking. And let me show you why I say that. Okay, my friends, I have a tiny little lung in the microscope. That is the spur lock, the triangle that locks it in. It latches right there aggressively into this, and this latches over. And I believe there's like two little tubes that run the fluids that were in this fabric bag, which is gone. We're down at the alveoli. You see, well, that's why you have all these different colors. Let me see if I can tune that in a little better. You see all these different colors? Those are different alveoli. And I showed you before that that's what happens. Blood congregates into its colors well, let me show you what happens in a heart that was saturated in blood. Now, this was a similar situation, but not quite as vibrant. Although I do have one that I cut and polished. Let me show you that one, and then I'll show you the heart, which is an opal that is just stunning. All right, check this out. This is outrageous. This is another lung. There's the spur lock. They all have it. It's a really gnarly, tough thing. Now, let me turn up the light a smidge more. Now, I cut this, so this is the outside. I'm going to tip it over, and we'll see the inside where it's cut, and all the passageways for all the blood and all of the new mineralization inside, because there was still blood in it. So you got a lot of colors. Okay, watch this now. The reason I'm showing you this shot with all this flashy looking stuff, that's because it's cut and polished. This is blood. All that is where blood was running, all that brown stuff. Now, if I put it on an angle, you'll be able to see all the colors. You see it? Those are all the transition metals that have turned to colors. But when you flash it like this, all you can see is, that's a pretty good shot right there. You see all these different colors? Those are all different transition metals. I showed you this, and that basically, which is inside the lung, as I showed you, has a spurlock, is basically the same thing you're seeing in this thing right here. And now look at this. This is a heart. But remember, these are the colors up here. And it depends on where it was in the body, too. If it was down and the blood ran down there, the heavy stuff collected. I'll show you the difference between where heavy blood collects and where the lighter blood rises to the top. All right, this is an extremely eroded lung. I don't know what kind of creature it's from, but it's definitely a lung. Now, I have it in the microscope. I don't want to move it. There's a microscope right there. I don't want to move it because I have it focused in quite well. Now, I have to turn the lights off for us to see this well. And those are the alveoli holes. So take a second to focus here. And that is the fabric of the lung, which has, you know, quite well eroded. But you can see, if you know you have Mudfossil eyes, you can see the fabric. And I'm going to come down closer so you can see it. But you can see the fabric. That's the fabric that coats the lung. Most of the black stuff is gone. Let me come a little closer, and we should be able to see a little better on that fabric. All right, you can easily see the alveoli holes. And this is the fabric. Let me back out the light a little bit. And then I'm going to put a little water on there, and that usually brings out some pretty good highlights. So let me just splash a little water on. Hold on. All right, this is the fabric of the lung, but it's eroded. It's eroded, and you can see down inside all the alveoli. But you can also see where the fabric had all those little white fibers attached to little black balls. You see? See all the white fibers? Now, that's exactly like my lung here. There was DNA tested and CAT scan. Hold on, don't forget. Isn't that amazing? That just blows my mind. That is exactly what the alveoli look like in a... Incredible. Where was I going to go here? We're looking at that. Oh, here's mine right here. You see that? That's the same stuff. Only it's not eroded like the other one was. The other one's just totally eroded. This one hasn't eroded at all. This one has completely eroded all the way down to here because it's filled with silicates. You see all the little alveoli holes? They all just filled in with silicates because it voided out except for the very outside, and then that got stripped away. Somehow, I don't know how. And this part here appears to me was laying like this, and the blood collected down here, and when it came out of the mud, this is what happened. Out of those little red spots, a few of them, they came out with actual blood. That's a blood ball. I don't care what you think of it any way you want. That's a lung, and there is the spurlock. They all have them, and there's the spurlock on this one. You know, if it all dried out and that's all you could see that was the strap left, it would be just like this one. Now, they show it on the anatomical, but they don't show it any different than like the outside layer of pleura. And that's what I asked a couple of anatomists and autopsy guys, and they say, oh, it's just fascia or pleura, wherever it is on the lung. On the lung, it's pleura because it's a big rubbery thing. In the body, primarily, it's fascia, which is membranes. But every membrane has to go into another membrane, and it does so through these there's little fluid tubes. I'm pretty sure. I can see them in a microscope. I'm almost positive. So there's new biology here. Plus, I pretty much found that fluid-filled highway in my mud fossils, and I couldn't account for it. And I did hook up with people that helped me to understand it. And that was long ago, 15 years ago, 10 years ago. Anyway, now, I told you how metals are heavier and they would sink, and lighter fluids would drift up. Can I prove that? Yes, I can. And at the same time, I can prove that transition metals find each other in fluidy, extremely transition metal heavy fluid conditions, and then they become solid opals. All right, these are the transition metal colors that are in your blood, and they are in the ligands. They carry it through aqueous solutions, and that, my friends, is that little lung that I showed you. And these are all, the alveoli have collected what they like as far as transition metals, and they bond with the silicates and form these crystals inside of those areas. And again, you see that? The polished parts are the crystals, and the brownish spots are the blood. This is a lung. There's no getting around it. And it has a spur lock on it somewhere on here. There it is right there. It's small, but this is what it is. And that's the little latch that holds it in place, which they all have. And it's totally different than everything else on that surface. And at this point, it's not understood that that is a different material. That little flap, and it's on all of the lungs that I have here, 100%, even one that I'll show you that came through space. Okay, my friends, this is a fabulous article. The elusive roles of metals in human health. It's not elusive, they are the carriers of everything in the body. The ligands form around them as the metal core. And they say 2.5% of the human body is made up of metals, which is not a lot, but they do all the carrying in the blood primarily. And they have to be correctly distributed between organs, across tissues, even within cells. They're everywhere. They're everywhere. Now, this is going to be the most important part right here. All right. The interface between bio, which is living things, and chemical cell biology of the sponge, whatever that is, molecules, and the bio-inorganic chemistry of metals, inorganic, they're the transition metals, offers vast potential for improving human health. Metalomics, this is something new apparently, has already revealed that metals are implicated in processes previously thought to proceed without them. They thought metals were just, I don't know what they thought. It's now thought that around 50% of human proteins require a metal ion to function. Proteins are the enzymes. They're the exotic chemicals, very exotic chemicals. Now, they're saying the holy grail of metalomics. Modern analytical techniques are becoming both sensitive and specific enough to detect almost all the essential metals. And Theodora Stewart's recent perspective article published in RSC journal Metalomics offers a comprehensive insight into the multitude of techniques available in the Metalomics toolkit, which is to look at things and try to understand them. That's fabulous. Now, the holy grail of Metalomics is determining the identities and quantities of metal species in a location in the body at a certain time, and how these change over a period of time. whilst obtaining enough information with just one measurement or analytic technique is impossible. You got to look at all, over a course of time. The combination of methods can be an incredibly powerful way to achieve this goal. What they really should be doing, and this metallomics is fantastic, but metallomics are involved in enzymes. Enzymes require bacteria. Start with the bacteria. See what bacteria are available, and then see what metallomics are in the guy's body. And I'm going to tell you right now, there's virtually no question whatsoever. The bacteria level is going to affect the metals that are in the body. It's just enzymes. It's called half-life decay. And they can decay down and they can decay up, but they require enzymes to do that. Working with the half-lives is so fast that you can't do it. It'll just take forever. Because all the half-life is good for, even minutes is too long. You got to go instantaneously. They work 1,000,000 times faster in most cases than actual normal, molecules changing. They change just like they do with the enzyme, but they just take forever to do it. You die. All right, I think I probably bored you half to death by now, but this is a heart that was opalized. It's opal. It's from Yoa region in Australia. And you see all these colors? Those are all the different transition metals. And why are they in specific types of membranes and so forth? Like this wants to be with the blue, quite obviously. And it is attaching to that because that's where it finds stability. It's a charged particle, but it can't go anywhere to discharge. So it has to attach to something to find stability, and it did. And it attached to here. Now, this was a heart, and it is a complete heart, and they cut it in half, and it was laying this way. And you say, well, Roger, how do you know that? Well, because this side was down, and I know that because there's the metals. I showed you the transition metals. They're up in here, and they're up in the heavier stuff. Plasma is just almost mostly water with a little bit of red. You see up here? There's almost no metals up in here. They all drifted to the bottom. So it was laying that way. So anyway, that's why opals form this way. They have to be in a certain area and and they have to have a certain chemistry and they have to be for a long time. But the primary thing is they have to have a ton of blood, which is transition metals. And like I always say, Australia to me looks like just one gigantic scab. It's just completely red blood. So anyway, that's what we got, my friends. And I don't know where else I can go with this because I've shown you everything here. What I want you to remember is, don't forget now, this is Bennu is a heart. They came back with this stuff from Bennu. This is asteroid Bennu. They came back with this. This is phosphates, which is they're glowing here because they have it under a certain light, and it shows up as white, which is the membrane. And they said, whoa, we never expected that. And right below the membrane is the muscle sarcomeres. There's no question. And they have this stuff right here on Earth. They came back from Bennu. And Bennu is a heart. That is absolutely certain. Now, I want you to start talking about this. Confront people. We're spending billions of dollars walking around in a circle. That is a tubing coming out of it. That's another tube coming out. These colors are the colors of blood. These are valves, the heart valves. This is a heart, and so is Psyche. You see Psyche over here? That's another heart. And it's cooked into metals because it must have gotten close to the sun or something. And it heated it up so hot that it started to smelt. Now, Bennu has not smelted at all, but they are both hearts. If you can't see this, plus they have this back here on Earth, and they have the sarcomeres. They're actually sarcomeres. You can't miss it. And they said, we never expected to find phosphates. Well, phosphates are the membranes, phospholipid membranes. And there's a membrane on each side of these sarcomeres. No, I'm not going to get crazy because I've done this a bazillion times. Each one of these blocks is a sarcomere. This is damaged heart muscle because it's torn. It's supposed to be sealed just like that everywhere. It's torn here, torn here. But these are the blocks. And they are the sarcomeres and in between is the phosphates. Like that little white layer in between is the phosphates, exactly as they show here. Hold on, phosphate surprise. How did that happen? Where did phosphate come from? I have no idea, but it's loaded with iron oxides, which is blood, iron sulfides, which is from blood, carbonates, which is we are carbon-based creatures, and that's all it is. And it was clay. Clay is what mud is clay, and mud is eroded flesh. And here's a phosphate layer right there. And below it is the muscle sarcomeres, and below that is another phosphate layer because they have layers after layer so that the muscles can slide in among themselves. All right, remember what you're looking at. This is the phosphate layer, and then you have sarcomeres. Then you have a phosphate layer, and then sarcomeres. This is up at the top edge of the heart muscle where it's, there's no more sarcomeres above here. But this is the way they have these lines in between them, which are identical to what you see, what they brought back. I knew it was a heart when it was up there. I just been saying, I said, when you come back, that is going to be a heart, and it's going to be blood. I didn't realize they come back with sarcomeres. That's pretty nice of them to do that. But this is the phosphate layer, which is on top of this. You don't see this with the naked eye. They put a different filter on the light, so we can see it's coated with phosphate, which is the membrane. And now I'm going to look at a little piece of this, which is over here, and they're looking down inside of it, looking real. Now they're getting real close, and what do they see? Sarcomeres. Those are the muscle sarcomeres, and there is a membrane under it, and there was a membrane over. You see over here? There's the membrane over the top, which would have come all the way over here. It's peeled back. And then this starts another layer of muscle up above it. That's what heart muscles are made like. And it says a tiny fraction of the asteroid Bennu sample returned by NASA, shown in microscopic images. The top left pane shows a dark Bennu particle here, about 1 millimeter long, with an outer crust of bright phosphate. The crust. That's the membrane. The other three panels show progressively zoomed in of that until you get right down to the sarcomeres. That cannot be denied. And the chemistry is there. The chemistry, I'm telling you, the chemistry will be identical to a heart chemistry of just about any creature, heart muscles. And these are what the heart muscles look like. Right here, there they are. Those are little blocks. And they just grabbed a bunch of it and came back with it. And you can see these blocks laying sideways, but right in between there is the phosphate layer, which separates it. I think I made my case once again. Shocker du jour, Mudfossil University. If you see something here that you didn't think you want to agree with, certainly tell me and say, Roger, you missed this or you missed that. But watch it first. I don't want to hear some screaming that I missed everything, and then because people don't look. And again, this is what a heart looks like. It has rope muscle, but it twists. And it goes like squeezing out, pulling back, squeezing out, pulling back, but it's a twisting motion. And these are like rope style muscles, and they're like this, but each one of them is a sarcomere, one right after another, and they all twist and all like this throughout the heart. Oh, there's just a ton of muscles, a ton of them, and it's just loaded with blood. That's what a heart is. And that, my friends, is a heart with the plumbing off the top removed. This plumbing goes off. This is glue, literal glue. The heart can do all this. It's always doing like this. And that's going, but the plumbing comes out and goes to where it has to go. But this goes, and then eventually when it gets out in space and dries out, or gets cooked or whatever, that dries up and then this plumbing goes off. Right there. And see these little tubes running out? These tubes are running out of these here. Same thing. There's no difference whatsoever. None. This is the tendon. Right there, there's the tendon. You see it? Tendon doesn't run off like the gooey stuff. The tendon gets still stuck here. And that reaches around and holds onto the muscle. It's actually, like I say, it's this kind of a thing. And this is just saturated with blood because it's a heart, first of all. Secondly, this muscle is almost all blood. The muscle has, of course, it has the connective tissues and the fibers and all that, but there's just so much blood in there. And again, I think I mentioned it several times, your heart pumps 1.6 gallons of blood per hour just sitting around doing nothing. And when you get running and your heart's thumping like crazy, it's much more than that. I think it was 5 or 6 gallons a minute. Okay, I'm going to probably close this up pretty quick. This is a meteorite. I've shown this a million times. Cut in half, etched, showing all the different types of metals. And then there's this red blood. And then there's this black blood, which we all know now, if you're a Mudfossil person, red is artery, black is a vein. And this is inside of a solid metal meteorite. So that's kind of interesting. I know why. I believe this was a liver. You see that? That's blood. That's blood. And that is the other side of the blood. You got to have red coming in and black going back out. You see this? Oldest solid material in the solar system. Who says that? Chondrules. This is another meteorite. That's red blood. That's the artery. And this is probably where the vein blood was, but I'm pretty sure that's where the artery was. All these little chondrules, those are like tendon enthesis balls. This is not the oldest. Who knows what it is, but it's certainly not what it's being portrayed as. All right, this is the microscope. I got this little magnetic along. You see how it's iron, and it holds onto the magnet pretty good. Now, I'm going to put this in. It's in the microscope now, and you'll see this. I'm going to take the magnet off, and we're going to look at what's happening there in a Z microscope. So up there is a Z microscope. I have to turn off a Z light. Alright, now that it will take a second to sink in. All of those little brown holes are alveoli. And this thing cooked off coming through space. Hold on, I got too much light. So we'll take that down a notch. And I got to focus better. Alright, I'm way off. Way off of this. But you get a really good look at it with the lighting and the way it works. You see these little white specks? Those are the fabrics. Usually there'd be a ton of those, but they burnt off. The black cooks into just solid and very, well, not very hard, but pretty hard. Now inside is the alveoli, and I can come down there and you can see it quite well. Now here's the structure. The lung comes up right up here, and you see all that special little stuff up at the top there. Where they hook in to the next body part, there's a lot of structural things going on. And on the other end too, I'll show you the spur lock, which is on the other end. Now, I'm going to put a little water on here, and you'll see how dramatically it changes. Here we go. All right, now, let me dry that up just a smidge and put a little more light on the subject. It's a cooked off little lung. Alright? And these are, again, these are the little fibers. And these are all the little channels through the lung. Now I'm going to find some other spots on here. There's some really excellent places to look. Let's see. Let's do this together, my friends. Well, you know what? Let me show you the spur lock. I always say there's a spur lock on every lung. And here it is. Hold on. I got to put it in a Z clamp. It is right there. Alright, there it is. That right there is the spur lock. That triangle right there. Let me come way up off of it so you can see the whole thing in its perspective. Alright, I think you can see that, I hope. That's the triangle right there, and it locks in real gnarly stuff. Let me put some more light on this. And they all have that circle. They have that's what's invested in, and then this tips into the next place. You see the circle? And this is all really gnarly stuff back here too. All that latches the lung into the body. And you see up here all this, that's all part of that tag right there. So that it won't rip out of your body. You see how they have that little angle looking thing coming down there? They all have that same look to them. And I believe those two little lines there, right here, let me see, oops, let me see if I can tune this in. I believe those two little lines coming right down the center feed the next organ with the fluids. And this is where it's gnarly. It's tough there. And there's a little tab right there that locks into the next flap. Because there's only going to be another flap. This lays on the other flap. It's like a snap, almost like a button. I'm not kidding you. It reminds me of a button. And these two little jobbers there transfer the fluids. I'm almost certain of that. I see it on every one. Okay, I said I was going to do the new mini moon and show it in great detail, and I believe this is it right here, which is a kidney. And that is the plumbing, this little round tube area here that goes in. And there's another area here that blew out from one of these, just from laying flat like this over the course of time when it first petrified. But that's that circle right there where all that plumbing comes in. And I showed this, hold on, let me just show you 1 minute or so of this. This is 2024 again. And this is not, all right, this is the asteroid 2024. It's going to be orbiting like a little moon, they say. And it's, I believe it's a kidney. So I'm going to be showing my kidney against that kidney, and we'll go from there. But these straps, that's, you know, I understand this stuff pretty good. You'll see. Okay, I'm going to leave it on this, but this is outrageous. This is a kidney. All the plumbing comes in here. And you see this tube coming off? This is the area of the plumbing right here. That circle has all of this stuff coming in. And I looked at it in a microscope. I could see it pretty good. Now, you're going to have to use your Mudfossil eyes and pick up on that shadow. That's where all this stuff enters in. And that's where that tube comes running off the side. And one of these things blew out here. One of these areas. And that also we can look at in a microscope when I do a real good examination. And you see all these little straps and stuff? You see all those little strap looking things? I showed you that on the Comet 2024 or Asteroid 2024. They had the same straps. All these little straps down at the bottom, you see them? Straps and balls. You see that? Alright, I'm going to leave it at this. This is probably the best shot you're going to see of it. But this is the strapping, all that stuff right there. Let me see if this can open up. You see it? That's basically the same as this stuff right here. In a microscope, you'd see it's the same strappy looking stuff with all the little holes in it. Now, exactly what it does, I don't know for sure. But again, all my stuff pretty much is flat as a pancake on one side. You see all these little patterns and so forth? You have to know how to really read things. You see the circle? That's that circle right there where all that stuff comes in. And it even has that one tube running off. I'm sure that was that tube running off of that edge right there, as I showed you a while ago. One more look and off to the races. You see? That looks like that big jobber coming off and then just coming right off to the edge. But there's no question there's a circular pattern there. But you got to get it in the right light to see it correctly. And all that tubing went in, and I could see it in a microscope. And when we put water on it, you'll see the different colorations of the different blood and so forth. And the pattern. But again, this takes a while to understand and to look. I can see that very clearly, that circle. And that's where all the tubing goes inside to run it. All right, thank you. I love you all. Let's just keep doing this until it starts to go into the mainstream and people start to take, you know, this is really literally earth-shaking. I mean, this is literally earth-shaking stuff. And it's just being shoved into the back because academics hate it, because it proves God or something's going on that they have totally gone against, and not just missed, they've gone against. And the religious people don't like it because it shows that the mythology is pretty valid, which some of them see that as threatening. I see it as no. I see it as that Jesus Christ, if that's the one they're looking for, he came here to warn us. So you better pay attention. That's my advice to everybody. Pay attention. And, you know, you're here to learn. To my feeling, that's what it is. And nobody lives out forever. Well, maybe some gods and so forth. And you might make it too. And I might make it. I don't know. But I can tell you one thing. If you don't look and search and try to find knowledge, you're not going anywhere. You're certainly not going up. And that's, I'm seeing everything is either go up, you go down, or you stay the same, do it over again. Only this time, who knows what's going to happen to you. You know, you made it through this time, somehow. And what about the next time? You could be in Gaza or somewhere. I mean, this is, the things that happen to people are just horrifying. Absolutely horrifying. And, I don't want to dwell on that, but if you learn from that, hopefully maybe that'll lead you to a better existence in the afterlife. I don't know anymore. I really don't know. All I can tell you is I had no religious inclinations whatsoever until I found the mud fossils. And then as I kept searching, everything I found pointed to the fact that Jesus Christ appears to be exactly what he said he was. And the physical evidence support that, plus Apollodorus and all of the ancient texts and the mud fossils and Velikovsky, all the stories of gods and dragons and monsters and giants and a global flood and all, it just all fits together so flawlessly. But what is Jesus' role in this whole thing? The only thing I can take out of it is he came here to warn us and said, I can't talk to you straight out because you're never going to believe it. And even in the Nag Hammadi text, it says, search until you find, and when you find, you're going to be disturbed, and you will marvel. And then he also said the earth is a corpse, and the earth is a body. He who finds the earth, or finds the world. Now, what he meant by world, that's in a dispute. But he who finds the world has found a body. And he who finds the world has found a corpse. Search until you find, and you're going to be disturbed, and you're going to marvel. And then the other one he said was, we are made of light. We are the children of light. And all of these things I have discovered, I found them, absolutely no question, all of those statements are true statements. And he's the one that said them. I go with Jesus Christ. And all the other things he said, I'm going to have to figure were probably pretty true. I mean, I don't think he'd be lying. Do you? I know. So if you accept all that other stuff, that he's the one that said all these things, and they were all true, nobody would have believed them. And that's why he had to speak in parables. He'd say this and that, and they'd say, what do you mean by that? He said, well, you think about it. And, because it's like Enoch, the book of Enoch. The giants are 2.5 miles tall, and the 7-headed dragons and monsters and Apollodorus and all these people, Hesiod. Nobody's going to believe that stuff. That's why they just pushed it off to the side and said, go down the middle, talk about a guy like 12 feet tall, he got hit in the head with a stone, call him Samson, and whatever. I don't know what to believe actually occurred, but I can tell you what actually is on the face of the planet, and it is giants and dragons. And Apollodorus, exactly what was written in Apollodorus 1.6.2 and 3, talk about Typhon attacking the gods, and Ares turned herself into a fish, or his whoever it was, turned himself into a fish, and Typhon attacked him. And it's all written. It's not. It's just too. It can't be a coincidence. Obviously, just think about it. And it says how long he was, and his red eye, flared eye, and this and that, and he had the thighs of a human and coils. And I found every single one of those things. The only thing I haven't found was all the extra heads. And they say they were on the tips of his coils or something, so they got destroyed. Yeah. Okay, that was the Commander-in-Chief calling, so I have to go. I love you all. Pay attention to the details. This is real. This is earth-shattering stuff. If you hear this stuff and it resonates with you, it is incumbent on you, which means you must relay this information. If you want to follow what Jesus has said, he said, go out and say these things. Tell the people what's going on. They have been misled. And you're being misled right now. It's unbelievable, to be honest. Anyway, I'll get in trouble if I don't get moving. All right, I love you all. Talk to you later. Thank you. Bye.